top is edge minimal graphs with generalized Quaternion automorphism group. Lindsey-Kay, Lauderdale, Christina Stephen Graves from Towson University.
Thank you very much for having me. So today I'm going to talk about edge minimal graphs with a generalized Quaternion automorphism group. And this is joint work with Christina Graves and Stephen Graves, who are at the University of Texas at Tyler. So I'll start with a definition, and I'll let gamma be a graph. Throughout this talk, I'm going to assume that all graphs have no loops and no multiple edges between two vertices. So the automorphism group of gamma is the set of adjacency preserving permutations of the vertices. So I have a few small examples. When we're computing the automorphism group of a graph, one thing we can do is look at the degree of each vertex. Since the automorphism group is going to preserve the adjacencies, the degree a vertex must map to a vertex of the same degree. So in this little toy example, we have one vertex of degree 3, so it'll have to be fixed. All right. In turn, its neighbors will form an invariant set, but only one of its neighbors has degree 2. So if the 3 will be fixed and 4 will be fixed, then 5 will be fixed. And so the only thing we're allowed to do here is interchange vertices 1 and 2. So the automorphism group of this graph is isomorphic to a cyclic group of order 2. All right. In this particular example, every vertex has degree 2. They all look the same. So if we pick one vertex, we can map it to any 4 of the other vertices. Right. From there, we can either switch its neighbors or leave them in the same order. Okay, so we should expect to have 8 different automorphisms, right? And indeed we do have them here. So this is the graph we started with before. We can rotate 90 degrees, 9 degrees, 9 degrees, and then flip everything down. So the automorphism group of the square is the dihedral group of order 8. You can play a similar game with this graph. It has 16 vertices and 44 edges. Its automorphism group is the Quaternion group of order 8. So we won't go through that, but it's a similar argument. So in those 3 examples, we saw graphs that had a cyclic automorphism group of order 2, right, a dihedral automorphism group of order 8, and then the Quaternion group Q8. So it might be natural to ask, can we realize any other groups in this way? And Frug answered this question in 1939. Every group can be realized in this way. All right, so if you give me a group, I can construct a graph that has the desired automorphism group. Once I have that graph, I can make simple modifications to it and increase the number of vertices or the number of edges as large as I like. Okay, so the number of vertices or the number of edges can grow without bound with a fixed automorphism group. So it's more interesting to investigate how small these graphs can be. So I'm interested in this talk in edge minimal graphs. So we'll define this invariant here, right, E of GM, and it's going to denote the minimal number of edges of a graph that has m vertices and automorphism group isomorphic to G. If no such graph exists, then we're just going to consider this invariant to be undefined. So the minimal line problem, line here indicating the edge in the graph, is to determine the value of E of GM for each positive integer. And originally, this was posed by Erdos and Renee for graphs that have no non-trivial automorphisms or asymmetric graphs. So here I have 3 examples of asymmetric graphs. This one here only has 1 vertex, so it's asymmetric. And this one here has 6 vertices and 6 edges. You can play a similar game to the previous examples where you look at the vertices of degree 3, right? they would have to map to a vertex of degree 3 under any automorphism. And so this is the only vertex of degree 3 that's adjacent to a vertex of degree 1. So kind of dominoes through, and you have to fix everything. Once you fix 2, and you have a similar argument for this one down here. All right, so Quintus was able to solve the minimal line problem for the trivial group. And so the first few cases are special cases. Okay, so if we have a positive integer less than 7, right, then if you have one vertex, you don't need any edges to have a graph that's asymmetric. Right? If you have 2, 3, 4, or 5 vertices, then you cannot construct an asymmetric graph. And if you have 6 or 7 vertices in your graph, then you need 6 edges. So if we come back to the previous asymmetric graphs, so this isolated vertex here is establishing that E of the trivial group on one vertex, that should be a 0 there, right? 0 edges. See, I think all right, so this one over here, all right, oops. We have this trivial group here. It's on 6 vertices, and we have 6 edges, okay? And this example here is indicating that it's not edge minimal, all right? We have more than 6 edges for this particular graph. Right, so that is not the edge minimal asymmetric graph on 7 vertices. All right, so those are the special cases. If M is larger than 7, then the edge minimal graph is going to depend on the number of asymmetric trees on n vertices, and so we'll denote that by an. So for each integer larger than or equal to 8, we're going to define 2 new integers. Capital N can be defined using these inequalities here. And then once you have capital N, along with M, we can define this W here. And so under these assumptions, if you want an asymmetric graph on M vertices, then this is the minimum number of edges that's required. So after this problem was solved for the trivial group, it was solved for a few other groups as well. So I've listed all of those groups here. We have the symmetric group, the cyclic group of order 3, some dihedral groups. The order has to be twice a prime power, so n or n over 2 is a prime power. And then it was also, the line minimal problem was also solved for octahedral groups. All right, these are symmetries of a hypercube. So we were interested in solving this minimal line problem for the Quaternion group and the generalized Quaternion group. And the way I've presented it so far, it's certainly not natural to consider the Quaternion group next, but this problem came up as part of another problem where it was natural to consider the Quaternion group. So this is the presentation I'll be using. The group has 2 generators, sigma and tau. Sigma has order 2 to the n minus 1, tau has order 4. If you conjugate sigma by tau, you're inverting sigma, and then lastly, sigma to this power is tau squared. So some basic properties that we use to solve the minimal line problem for the Quaternion group. All right, this group has order 2 to the n. It has only one element of order 2. And outside the cyclic group generated by sigma, everything has order 4. Right. Also, if you have some integer that's strictly less than 2 to the n, you can't embed it into the symmetric group Sk, where k is your number less than 2 to the n. All right, so if we're looking for a graph that has this Quaternion symmetry, all right, then one thing we want to note is that this group is indecomposable. So that means that we cannot write it as a direct product of two of its proper subgroups. All right, that's going to have implications on what the graph looks like. So this proposition here characterizes the automorphism group of disconnected graphs. But since our group is indecomposable, what that means is if we have some disconnected graph with Quaternion symmetry, we're going to have one component that has Quaternion symmetry, and any other component that's present in the graph would have to be asymmetric. Okay, so this lemma is going to allow us to solve the minimal line problem for small values of m. All right, so if we assume that we have some graph, gamma, whose automorphism group is isomorphic to the generalized Quaternion group, and we're going to assume that it's generated by sigma and tau, those generators I just presented. But remember, those generators are permutations of the vertices. Okay, so since they're permutations, in this particular case, we have to have sigma as a product of at least 4 2 to the n minus 1 cycles, and tau is a product of at least 2 to the n minus 1 4 cycles. Okay, so this is giving us an idea of how large the support of these permutations have to be. So using this lemma, we get this theorem, and this one holds for n greater than or equal to 3. The value of E of the Quaternion group M is undefined when M is less than 2 to the n plus 1. And that's because if we're going to have a graph with Quaternion symmetry, this generator sigma needs at least 4 2 to the n minus 1 cycles. It's possible it has other things present, other cycles present, but we need at least that many. Okay, so what happens if m is larger or equal to this value or slightly larger? Okay, so this is where Q8 becomes its own special case. All right, so I've put some small values here. All right, and I've included some small values of Q8 because it's the only group for which the line minimal problem is solved that has this property where it's decreasing and then increasing and decreasing again. All of the other ones are increasing. So yeah, there's that. It's the special case. All of the other Quaternion groups follow a pattern like this where this invariant looks like an increasing function. All right, so I've left out the special case of Q8, so we're going to assume that n is at least 4. Okay, so there are some special cases, but from some point on, okay, we're getting this as the minimal number of edges we need for a graph to have Quaternion symmetry on m vertices. And so these edges here are coming from a graph that has Quaternion symmetry. And then the edges coming from here, all right, are going to correspond to other asymmetric components in our graph. Okay. So I'd like to take a few minutes to explain how you might construct a graph with Quaternion symmetry corresponding to this number of edges in our E of q to the 2n m. Okay, so I'll do this construction in general, and then we'll do it for an example. So the idea to construct this graph with Quaternion symmetry is we're going to construct two subgraphs. All right? Each of those subgraphs are going to have vertices labeled from a Quaternion group. All right? Then we're going to connect those two subgraphs up in a special way so that we're destroying some symmetries and we're getting the Quaternion automorphism group that we desire. Okay, so just for notational convenience, I'll let m be 2 to the n minus 1. And so this first subgraph, we're going to define gamma 1, right? We'll have the vertex set listed here. All right? And so those elements form their own Quaternion group. And the edges in this graph are going to look like this. So for every element of the group, I'm going to connect things that look like G, comma, GY. So that's the first subgraph. In order to construct the other subgraph, we're going to have an isomorphism from the Quaternion group to itself. And I'm going to send this element X to A and the element Y here to B. Okay? So essentially just relabeling those vertices. We're still having a Quaternion group. And just so we don't have two vertices labeled 1, we're going to let A to the 0 be denoted by 1 bar. So, all right, this other vertex set in the subgraph gamma 2, all right, will just be this isomorphism of our Quaternion group. So we have another copy of the Quaternion group labeling our edges in the graph. Those vertices in gamma 2 are not connected. Okay, so I have 2 graphs. Each are labeled with elements from Quaternion groups. I'm going to union those 2 graphs together. And then I'm going to connect them using edges of this form. So edges that look like G, H, C, and C will be 1 bar, so the identity in that group, A and B. Okay. So this graph has 2 to the n plus 1 vertices because it's got those 2 copies of the Quaternion group. And then this is our desired number of edges. All right, that was coming from our enumeration in the line minimal problem for the Quaternion group. Okay, so I have an example of that construction. I just picked n equals 4, so we're looking for 64 edges as part of Q16. So this is 1 copy of Q16, so I'll have the powers of x here, all right, and then each of those powers of x times y appear here, and I'm going to add in the edges that look like this form, G, G, Y. So for example, if G was 1, I've connected 1 and Y with an edge. If G was X, we've connected X and XY with an edge, and so on. Now, gamma 2, all right. So essentially what we've done is we just have a new copy of the Quaternion group. We've relabeled all of the X's with A's and all of the Y's with B's, and we have no edges in this case. Okay? So now we're going to put those 2 together. So I now have all 32 vertices here. And we want to include the edges from gamma 1. All right, so I've done that here. In addition to those edges from gamma 1, I want to add in 3 more types of edges. So we're going to add in edges that look like G times H. Okay, so that's going to connect 1 and 1 bar, A and X, A squared and X squared, and so on. So that will look like this. Next, we want to connect edges of this form. Okay, so GHA. And then finally, so that we have 2 to the n plus 2 edges, we're going to include edges of this form. So this is the construction of our graph, and it has Quaternion symmetry. Okay, so why does it have Quaternion symmetry? Okay, well, the way I constructed it, I made sure to embed the generalized Quaternion group as a subgroup. Okay, so we get that it's a subgroup for free. I've written down these permutations, sigma and tau, that generate the quaternion group. So I know it's a subgroup. Well, how do I know that that subgroup is actually the entire group? Okay, well, you can take a look at the orbit stabilizer theorem. So if you pick any vertex in that graph, okay, I've called it G, all right, you can look at the induced subgraph, and you'll notice that in that induced subgraph, there's one vertex that has degree 1, so under any automorphism, it would get mapped to itself, assuming that I fix G, right? On the surface, it's then possible that we could interchange these two pieces here. However, if you look at the next layer of vertices in this graph, you get something that looks like this. And in this second layer here, we have one vertex of degree 4, so it was fixed. And then you can use a similar argument to argue that actually all of the vertices are fixed, assuming that G was fixed. All right, so if you fix, one vertex, you've destroyed all of the other automorphisms, and you're just left with the trivial automorphism. So that graph that we constructed does really have the desired automorphism group. Okay, so I'll have a few open questions. What else might you consider about this minimal line problem? Well, most of the graphs that were constructed were disconnected. So what happens if you insist that your graph is connected? So you can define a similar invariant, E sub C of GM, where you insist that your graph has to be connected. And then, you might investigate, well, what is this invariant? It's certainly going to be strictly larger in most cases than our enumeration of E of GM. You might also consider taking a look at these two invariants for other groups. All right, so these are all open. You might do a cyclic group of prime order. I guess P equals 2 and P equals 3 are done, but any other prime, a dihedral group, an abelian group, and an alternating group. Something more general, if you were to consider this invariant as a function of m, you might wonder, well, what integer m is going to minimize this function? So assuming that it's defined, what integer m minimizes it? And then does that correspond to a vertex minimal graph? In the case of Q8, this is the only known example, where you're getting this sort of discrepancy. If you minimize vertices first, right, you get something different than if you minimize edges first. That's all I have. Questions? Yes?
So I have a potentially long question. Back when you were showing the examples of it for Q16 and Q32, and listing them off for various m's, I noticed that a number of the numbers that you had there had like lots of divisibility properties, lots of them were divisible by 4 or higher power than 2, and then I think you had 41 in there. So do you know anything about whether or not, is there some property that's giving these like large amounts of 2 divisibility in them?
So that has to do with the fact that the group is a 2 group, so its order is a power of 2. Q8 is strange. It didn't behave like any of the other Quaternion groups, and it didn't behave like any of the other known groups where the line minimal problem has been solved. So I think it's natural that these are powers of 2 because, or divisible by 2, because if you have some edge in your graph and you're insisting that it has a quaternion symmetry, that edge will be mapped to an even number of things under some automorphism. So that's why, yeah, this this one here, you need this extra edge to destroy an extra symmetry. I don't know why that's odd. It's odd. Did I? Yeah.
Yeah. So perhaps I missed this, but you construct an example with the right automorphism group. How do you know that was minimal? That example.
So I didn't argue, because I only have 20 minutes, I didn't argue why that was minimal. But you can use the fact that the Quaternion group only has one element of order 2, and if you were to have any fewer edges, you can find 2 automorphisms of order 2. But I didn't say why that was true, because there's a 20 minutes is not a lot of time.
So the intuition in terms of the transformations that make the edges. So
do I have intuition on how to?
Yeah. How do you choose?
So, so once you figure out how many vertices you have, you know, you can start with a graph that looks like this. So this has the symmetric group as its automorphism group, and then you can start adding in edge orbits. So if you add in one edge and you know your automorphism group, you know everywhere else that has to map. Yeah. And so from there you can start adding in edge orbits and destroying the automorphisms going down from the symmetric group to the Quaternion group. Yeah.
This thing's speaker was wrong.